sounds good. And I wanted to show, first of all, I just wanted to show this picture because it's in your textbook, and I wasn't sure if Ramon was gonna show it or not, so I did put it in my slide presentation. But anyway, this picture shows you know, geomorphic features along the San Andreas Fault, and it's really pretty incredible because I always thought it was a pretty cool picture when I first saw it. But then as I started doing mapping on more strike slip faults, it's really pretty incredible that it holds pretty true for no matter what size of fault you have. You get these sort of landforms forming, and you know, they're larger and more extensive on faster slip rate faults, but on slower slip rate faults, these same kind of features are present. So, you know, we were looking at some of these things like Wallace Creek in the homework, but just some of these features like parallel ridges up in the mountainside and uphill and downhill facing scarps. We see these things over and over again along strike slip faults. And so I just wanted to clue your eyes into that, because what I'm going to do today is show you some data that's not super great from the Denali Fault in Alaska, and some of the first LiDAR that came out that was actually pretty pixelated once it was processed almost 20 years ago now. 2004, I think, was the LiDAR data set in Northern California that I mapped on. So, you know, it's not always the awesome, pretty LiDAR that Ramon was showing. So I just wanted to kind of caveat it that way. But the purpose is that when we're mapping, we don't always have the best data. And so I wanted to show some examples of what we've done with different data sets. So let me start slideshow here. Okay, so this is, so I'm going to talk about the Denali Fault in Alaska and show some of these features. So it's really tough to work here. Here's a helicopter for scale. You really can't do much there without a helicopter. I know Tim's been there to this exact spot, if you recognize it. I'll show a close up of this later. But anyway, it's really tough to work there, so you need a helicopter to get there. And it's a high alpine environment. And I showed this slide the other day where we talked about reverse faults in the Fork, the Castle Fault up here north of Anchorage, north of the Aleutian subduction zone. But today I'm going to show some examples from the Denali Fault, strike slip fault that extends through the Alaska range. So in this area, you get the subduction zone at 55 millimeters per year coming into and colliding into southern Alaska. A lot of that slips carried along the Fairweather Fault, which is largely offshore, shown right here in the lower right, which is really similar actually to the San Andreas Fault that we've been talking about. It has a lot of similar types of features on the seafloor, which makes it tough for us to study them, but they're there, and they've things like that. I won't show any examples of that. But slip along that is then partitioned into the building of the Chugach Mountains and then into the Alaska range along the Denali Fault. And so the Denali Fault moves at about 10 millimeters per year, and it's responsible that in a left step, Ramon was talking about compressional steps and bends and jogs. It's responsible for growing Mount Denali, which is about 26,000 feet. So, and that's right in the core of the Alaska range. Let's see. Okay, so zooming in, a couple things you can notice. This one on the top is that the Denali Fault basically just extends along long linear valleys within the range for almost its entire length. Other features are like pieces of bedrock and mountainsides seem cut off, like over here on the right and over here on the left. And then also just pieces of mountainous topography on either side that don't necessarily match up. Looking a little closer, you can see these long linear valleys extending along the fault. Just following my cursor here by the Richardson Highway here, and then out towards the Parks Highway. And I'll show some magnitude 7.9 earthquake, which initiated over here near the Susitna Glacier Thrust and extended about 346 kilometers to the east. So a really big earthquake. We know the fault was capable of large earthquakes. So example place has not occurred in 2002. So here's some IFSAR data. It's 5-meter IFSAR data. A couple things, a couple features you can see in it are sort of juxtaposition of different bedrocks along these little valleys, linear troughs. And then also you start to be able to pick out some of the deposits, and there's scarps coming across the deposits. I'll show air photos. So when we did this mapping, we made a quaternary geologic map of these glacial troughs and mapping these avalanche fans that extend across the fault, some of which are offset. I'll show examples of the air photos, but this is kind of some of the data that we started with was this IFSAR data. When you zoom in, you can see scarps across some of these quaternary deposits that are kind of coming out of these valleys and into the glacial trough. So this is what it looks like from the helicopter. So,
hey, Rich, can I interrupt for just a sec? Because I love that map, and I don't know, my zoom's a little slow, but I just wanted to highlight for the class, like, you know, in the conversations I've been talking about, I've tended to emphasize the morphologic features, but what I like about what your map shows is some of these deposits and more the domains or the polygons that are defining the fault zone. So in other words, these, you know, this is kind of like a geomorphic map with sort of deposits mapped. And that is another important thing that the class should be aware of, because, you know, the morpho is part of the story, but here the deposits are really valuable. So this is a really pretty map, and just want to emphasize that.
Right. So thanks. So yeah, my internet cut out for a second, so I apologize for that. But yeah. So, you know, we're not making return maps like this going in this per se. You really want to think about what deposits are being offset, and you know, some are offset more than others. Some show more morphology as opposed to others, which gives you an idea of their relative age, and just helps us understand the history of faulting in the area.
Would one of those
okay, so I'll show another slide about.
Oh, sorry. Would one of those offsets be like up to the upper right, where I think one of those fans are offset? The top section's off to the right, and the bottom's kind of sagging to the left.
Gone down.
Right. Yep, right here.
I think Joe's showing this annotation. Some of the edges of the fans are offset, like right in here, and then
yes,
yeah,
they are. So the quaternary geologic map does show where that's where we can actually see them, you know. And you know, when you zoom in on this IFSAR data, you can that stuff. I'll show some photos of air photos. Really, we look at them and still in stereo when we can, you know, and you can really zoom in pretty close with your eye and really see those things. So kind of using both data sets, the air photos and IFSAR together, kind of gives a perspective of where the offsets are. So I'll show details of this in a second, but this is just some images from the helicopter, and it's a little hard to see. So on the left is a photo, and then on the right is an interpretation of that photo of where the faults are. And the main things to pull out is these little troughs along the mountainside are uphill facing scarps on this side of this fan and on this side of this fan, and those are mapped over here. And plus we had some field work to see this as well. But there's nice scarps cutting across the fan. In this example down here, there's this avalanche debris fan that looks fairly young, yet, and I will say that this event that produced a lot of these scarps is probably about 300 to 400 years old or so, so not 2002. But anyway, here again, there's uphill facing scarps along the mountain front. In some cases with snow still in the little troughs. And then left stepping in echelon fracture patterns of surface rupture going across the fan. And so Ramon showed some examples of that, some schematics of that. Here's a real life example of the sort of the left stepping nature of the rupture coming across the fan surface. So we look at this fan again. And so I know Tim's been to this site. This is about an 8-meter offset on this photo in the lower right of a stream channel. And there's 2 nice scarps cutting across the surface. So this is a photo from a helicopter, and you'd actually have to flip it 180. This is a photo from the air photo, but here's those 2 traces coming across the fan again. Whoops, let me go back. 2 traces coming across the fan again in the offset channel. And so what we did is made a differential GPS survey of this surface and slope maps and topo maps to begin to try to interpret offsets. By about 10 meters, so this has been abandoned. And then also the edge of the fan is also offset, where you kind of see these bushes, this kind of stippled black and white pattern is the edge of the fan. So that's about 43 meters also, and then that one channel is about 43 meters also. So some of the games and then when we do that, we get about 7 millimeters per year, plus or minus. Plus there's some slip from several other cases. So you would get close to the slip rate that's been published by other studies. Fine scale.
Rich, maybe turn off your video just so you're you don't break up quite as much.
Yeah, apologize for that. Let me know if I really bumble on one of these, but it's okay. So here's sort of the air photos that we used in mapping the Denali Fault here, and just some features so the fault extends east-west kind of across this photo here. Here's the fan we were just looking at right here. So I've gone through and just kind of put some red lines on some of the more prominent features. So uphill facing scarps, and then kind of in here in the center, there's a bunch of sort of left stepping and echelon scarps. And they show up as kind of dark toned colors, you know, along little sharp lineaments. There's also a few things that probably need some question marks. So up here on the mountainside, there's some similarly colored fractures or dark tones. So that's up here. And so that might get some question marks. Maybe they're landslides or sacklungs or something, but still features you can pick out in the air photos. Oops, sorry. Another thing is this is a rock avalanche here, and it seems to be cut by something here, but the sense of offset is opposite really. So that would be a question mark kind of thing. What's going on here? Maybe there's some kind of secondary trace along there. But anyway, this is a kind of, this is 163,000 scale black and white aerial photos. So then again, what we were talking about is starting to think about sort of where offsets might be, start to think about these different deposits. So along here, you have a nice big long linear trough, and there's pieces of bedrock that are essentially shutter ridges, like right here and right here, moving along the fault, and then other scarps here, and some sort of letting and echelon patterns going across here. So as we map, sort of, this is what I was saying earlier, sort of draw out the stream channel and maybe some of the deposits if it helps you in your own mind figure out where the fault is. So here's just a dramatic picture showing how subtle it really can be. This little tiny trough right here. You know, remember, you know, glaciers retreated. This is a huge moraine right here. Glaciers retreated out of this area about 9,000 years ago. So it's experienced a couple earthquakes, but it's still just a pretty subtle trough coming across this bedrock saddle area. And then I wanted to touch on this. So this is the Denali Fault along the Parks Highway, which is the site of a proposed gas pipeline. So we talk about for this class the width of deformation and what we can see. for planning for some pipeline design issues. So in this upper panel left, the Denali Fault is really clear in the light up here, nice sharp line. It's really clear on the other side of the Jack River drainage, nice pretty sharp line. But there are a few subtle details, like a little basin right here, a little small sag pond. There's a right offset of this stream channel over here. There's also some small sort of bedrock inconsistencies that are kind of off at an angle from the fault right here. And so you can see how I've mapped that below with traces on both sides of that little bedrock discontinuity, which is kind of like a baby shutter ridge. But when you look out in the valley, there's really nothing to help us. The sediments are younger than the last earthquake. So that presents a problem for pipeline design. And so what we've done here in this lower panel is kind of project the orientation of the faults from each side, and with some uncertainty there. Oh, I should also point out there's another sort of scarp up in this area, maybe a secondary feature that would be question marked. But then, so the pipeline is actually closer to this side of the valley. And so by sort of projecting along off this shutter ridge and this in the terrace, we get a pretty good combined with some that zone of intersection between the pipe and the fault zone. This is just a photo of that shutter ridge looking to the east. So in there right here, the helicopter is kind of small. And then here's just of that sag pond. So here, actually, this other way along the arc and this also the
Rich, it's kind of hard to hear you right now.
Yeah, I wonder, do we have, does anybody have the phone number for this Zoom handy?
I can find it.
Hey, Rich, can you hear us? Looks like we completely lost him. There, yeah, there you go.
He's out.
Yeah, let me just send also to him.
Oh, you found it.
Okay, sent him an email. I don't know if it'll help. Any questions? I think one of the cool things that Rich was showing was, of course, that pipeline example, but oh, there he is. Hey, Rich, can you hear us? I just sent you.
Yeah, I'm trying to call him as well.
Okay. I sent you that number.
Yeah. Yeah, I just need the meeting ID. There it is. Hold on. Sorry.
No, it's okay. It's like apocalypse up there.
All in the same boat.
Yep.
Hopefully it should connect with voice any second. Okay, can you hear me?
Yep, you sound much better.
Yeah, sorry about that.
It's all right.
Okay, so I'm trying to share my screen.
Yeah, it
here.
looks good.
Okay. And then, so I just had a few more slides on the Denali. And then I wanted to share a few things on the northern San Andreas.
Yeah, Sean says put your PC on mute. Oh yeah, you did. It looks like.
I think I did. I do hear a little echo. Put this on mute. Yeah, I think that's better. Okay. What a nightmare. Anyway, so the 2002 Denali fault rupture. I don't want to spend too much time on this because we're mapping kind of pre-rupture, but I did want to show the map. And then when you get close up, you see a lot of this left stepping and echelon sort of pattern, which is really common. And then a few just shots of what this, sometimes when we see stuff just from a modern rupture, you can put that in your mind's eye when you're mapping older ruptures or older geomorphology. So I just wanted to show some photos of the 2002 rupture. So here it is, this shadowed kind of ruffled tundra.
Hey, Rich, your PowerPoint's stuck. Maybe like get out of presentation mode, go to the new slide, and then go back.
Okay. Let me see.
It just says air photo mapping. It's that one example of yours here. There we go.
Really? Let's see. I can't tell if it's sharing or not. Let's see. Back to Zoom.
Not yet sharing.
Not sharing.
Yeah, I think it dropped me.
How big is that PowerPoint?
It's I sent it to Chelsea and it's on. It's
Okay.
just PDF. It's 5.
Yeah,
I'll get it.
Okay, now Rich, you're back.
And is it sharing?
Yeah, we see the word, the Zoom, and the homeworks. Yeah.
Do you see my PowerPoint now?
No, we see Microsoft Word. Class Zoom details.
That's definitely a lag because I already closed that. So
Here,
Now we see field photos 2002 rupture.
Yeah, so it looks like you caught up. Maybe go back one.
oh boy.
Unless you want Chelsea to.
I have your slides up, so if you want.
Yeah, if you just want to show, you have it up on the PDF.
Yep.
Maybe go
Yeah,
ahead.
if you just want to share it, and then I'll stop sharing. And then, if you just want to go, because we're going to run out of time, I just want to go to the San Andreas stuff. So where it's the slide that says San Andreas, Northern California. I'll just skip the field photos so we can look at them later. So is that up, Chelsea?
Yeah.
Can you see my screen?
Yeah.
Yeah, see the San Andreas Fault, Northern California.
Perfect. Okay, so I just wanted to point out that similar, up here in the northern coast range, you have this linear trough. This map on the left shows this linear trough on the DEM. And what I was saying earlier is drawing out the rivers and stuff can really provide some insight. So this little map down in the middle bottom shows these rivers coming in to the San Andreas Fault, making 90-degree turns and following along it. So this is the Gulala drainage, and then there's this drainage divide, or sometimes we call them wind gaps on smaller systems. But there's actually quaternary gravels in this drainage divide. And then to the north of that is the Garcia system, which also travels along a linear valley and has these tributaries coming in at 90 degrees. So by looking at the stream patterns, it helps really figure out where the fault is located. And then there's a bunch of aerial photographs here. This is an oblique one in the middle upper part, and then these two on the right. And what you can see here is this long linear valley.
So you can also see it's full of trees and really hard to deal with as far as mapping goes. But Lawson mapped up in here after 1906, and Brown and Wolf in the 70s mapped up in here, and they did a pretty good job at figuring out where the fault is, but we wanted to refine that a little bit when LiDAR data first came out. So what I really want to show is that, do you want to go to the next slide, Chelsea? Is these indicators of kind of geomorphic features that you can add to your map to help figure out where things are, where certain traces are. So there's a table here, you know, and there's abbreviations you can use for scarp, ponds, swampy depressions, you know, any kind of descriptor that you can think of that will help you identify these fault features. And remember that diagram I showed at the very beginning as well. But springs and linear valleys, linear drainages, swales, breaks and slopes, directions of uphill or downhill facing scarps, etc. You can add these to your maps. It's kind of a geomorphic way of understanding where the faults are. And then below down here, I just have some descriptions, ponds and swampy bogs, and then you can also number sites. So these are site numbers where those features exist. So there's just kind of two different ways to keep track of the geomorphic features as you go along. This photo on the left just shows how difficult it is to see things, but this is a little linear trough in the woods, in the redwood forest, and an uphill facing scarp on the right side. So then just three quick examples here to show sort of this is the pixelated LiDAR, some of the first LiDAR along the San Andreas Fault, and then interpreted maps with sites labeled. And you could zoom in on this on the PDF on your own computers to see what these say. But a nice left stepping pattern through here, and you can see that in these images.
Next slide.
So then next,
Chelsea, there you go.
Sorry. Yeah, sorry, I didn't say next slide. So anyway, this is what I was talking about, the left stepping pattern here, going from south to north. So next slide, this should be showing, what I wanted to show here is that the linear trough, a little small linear trough, does not necessarily follow the center of the valley. So it is extending along the southwestern side, uphill facing scarps and other geomorphic indicators. In the middle, sorry, I don't have a pointer right now because it's not my screen, but in the middle there's two prominent drainages that come together, and there's some ponded alluvium up against an uphill facing scarp. So there's just other features there that can be mapped and help denote the location of the fault. And then just one more example of this, showing the interpretation on the right. So if you want to go to the next one, which is the final slide, near Dottie Creek, again, the fault shows up as a nice, clear, darker gray tone on the left side of the main channel, and some of the complexities that have been interpreted by the workers are shown mapped in the red faults on the right. So yeah, so I apologize for the technical difficulties, but you can study these images in the PDF provided in the lecture notes, and zoom in on this LiDAR. The LiDAR is now much better up there. It's been reflown, but this is kind of some of the original LiDAR that we had when we did this mapping. So is there any questions there on these things? And sorry again for the technical difficulties.
I have a few, but I can wait until after 10:15.
Okay.
Unless nobody else does and you guys are finished.
Yeah, and I'm happy to hang out as long as anybody wants to hang out and chat about it. We're getting close to the end of class time.
Okay, great. So I had a big question. I had a question on your air photo mapping slide.
Mm-hmm.
Okay. Hey, Chelsea, could you go to his air photo mapping slide for us, please?
Two more.
This one?
Three more. Yeah, right here.
This one, I think, yeah, this one right here. So I see that you put this fault right there, right? And I was looking at that area, and I see this on the non-marked up slide, how you got it from this line right there. So
Yep.
there's a line right below it, right here, that goes down here. Did you not mark that because of this fan right here?
No, it's strictly just because I didn't mark everything. You know, I drew these in last night. These were interpreted, you know, in a product, in a map that we wrote a report on and stuff. But I just drew these in and left some out on purpose. I mean, this is just sort of to illustrate the process of identifying some of these features. You know, you could have subsidiary faults and secondary faults that branch and splay off the main one. But there could also be landslides and other features on the hill slope that may not be faults. So I was just trying to emphasize that, you know, you're drawing out the things you see, but then you may use some question marks and things on some of the features that don't necessarily connect up nicely.
Okay. All right. Great. And one more question on your, I'm sorry, I probably should have asked this when we were there, the LiDAR and field map. Sorry, we just escaped from that one. Jessica, could you go back to LiDAR field map?
California. Yes.
Yes. So I know that, oh wait, no, I think it's one more over. Yeah, this one right here. So this is gonna be kind of a challenge for me, is that when I see a lot of the streams, I automatically assume that there's probably a faulting system like close by, or that, you know, I assume that a lot of times the stream may be the fault. So this bend right here in the river, right? I wouldn't map this as like the fault trace where the purple line is, because there's no like topographic, like there's no like landforms around here that would signify this being a bend. Is that kind of like, I would look around this area? Is that kind of what I should be doing, is looking also like around the sides of the fault to see if there's any other landforms?
Yeah, you want to scan the whole area, really, but you want to especially look like kind of on the continuation of where you know it's a fault, like on the left side where this nice like little narrow linear trough is along the edge of the valley on the southwestern side of the valley. So you're projecting that to the south and see if you see anything in there. And there are places in the Guala drainage where the young alluvium is cut. I don't know if exactly in here. I think the mappers here on the right show it as pretty dotted through there. So there are places where the alluvium is younger than you know, has buried the 1906 rupture, which is basically a lot of this morphology has been related is related to the 1906 rupture. But there's also alluvial terraces and such in the valley that do preserve a scarp in other locations. So you just want to scan the whole alluvium and see if there's any indication of faulting, you know, along some linear trend. And typically that is going to be in the form of a small scarp.
Okay.
Yeah, one thing if I can add on that point is, you know, that channel or the valley bottom is obviously a young feature. It's accumulating sediment. So if you want to find evidence for faulting, you know it's going to be young, so it's going to only record maybe the last few events, which is interesting in some senses, but clearly these slopes on the left there that are a little bit older pieces of topography show more cumulative deformation, and that's another thing to think of. So that's why at least my eye would not initially be drawn to that active channel in the valley bottom.
Yeah, and like I was saying, that's just, I know that's my bias, you know, that I'm just like, oh, well, there's, you know, a big valley, there's probably a fault nearby. So I need to like kind of start focusing on training my eye to see those other kinds of formations, and like how this fault right here is cutting through the topography instead, like this fault.
Yeah.
Yeah, and that's why I like to show the sort of uninterpreted and then the interpreted, so you can kind of go back and forth with your eyes and say, oh, that's what those workers were thinking, you know, when they saw this data, right? So it's just practice looking for these features. And like I said before, the diagram I showed at the very beginning, that sort of textbook geomorph on along a strike slip fault, is really pretty amazing because it holds true in lots of different tectonic environments, lots of different slip rates. You still get a lot of the same features, just different scales, different places. But if you can clue your eyes into what that diagram is showing, and then what the landscape is showing in the fault that you're mapping, it helps.
Yeah, just trying to kind of see through the noise, kind of thing.
Yeah. Can we go back 2 slides, maybe, Chelsea, please? Right here. So I love this this geomorphic symbol codes, and to me, this is another vocabulary. You know how I keep saying like the morpho mapping has these patterns, but I really like what Rich is talking about, where you guys could use these geomorphic features and just start coding the landscape. And so you see in those maps how there's all these little dots. So again, any one of them, you could be like, well, it's kind of ambiguous. But once you systematically start tagging the whole landscape with, or at least the zone with these codes, then you're like, well, you know, the group of them, the ensemble of them, to me really indicates a high quality fault zone or a moderate quality one, or it's ambiguous, but maybe there's something there. So another good strategy.
Yeah, and then just to add to that, on the maps on the next slide, the faults are also coded with strong and weak and concealed. You can see in the legend up there. So at the time, that's the terminology we were using: concealed, weak, distinct, and strong. So we kind of had a little hierarchy of kind of the confidence that we had in that we were on the 1906 trace.
That's great.